So my name is, he said, like, is Thomas Ruehr. I'm with corporate research in KUKA. And today I want to talk a little bit also about corporate research, how our business works, so to say, to keep it a little bit interesting for more of the management perspective. And on the other hand, talk a lot about like how we manage to get ROS working on our mobile platform. Here on the left, you see a very old picture. It's kind of a 10-year challenge, I would say. Sea Turtle was released 2010. And actually, I think this was already foreshadowing today's event, because if you look there, you can see on the very left, there's a Fraunhofer IPA robot. But then on the top right, you see two orange arms. And actually, that was one of the robotic platforms I had in my previous job at TU Munich, the ROS-I. And actually, that was a mobile platform manufactured by KUKA as a prototype, running with two arms, and we managed to control it via ROS. Well, at least it was enough ROS to be included in this picture, because actually we started out with YARP, and then later, when we figured out how cool ROS is actually, we wrapped the YARP in ROS. So it was good enough for Brian Gerke back then to say it's a ROS platform and include it in this picture. And yeah, as you can see, unfortunately, somehow ROS-I lost not only one of its arms, but also the head. And now at least we want to make sure we still have a ROS driver, right? So to be a little bit fair to that platform. And yeah, so I will speak about a little bit about technology rather to the end, but first let's start a little bit. I'm sorry for this. Everybody plays this game of doing a little trade show, so I had to include 1-2 slides about KUKA. I guess you all know KUKA, and I think what's important to know is actually that we have kind of an integrator side of things, KUKA systems. So mostly like large-scale welding lines and things like that are done, like, how do you say, turnkey ready for automotive. So if you have a project like this, you can come to us. And there, we're actually not only using KUKA robots. So it could be that a customer has some other robots, or he's choosing to have some ABB robots. So we actually have specialists in all kinds of robotic manufacturers and integrating them in ourselves if it's wanted. And I think that gives us a very good insight on the integrator business. And then a large part, like the other 40%, so to say, is KUKA Robotics, which manufactures the robots, but also standardized sales. So we have a lot of businesses where like tasks are very similar. You have something that you want to weld, now you need a welding cell, and then we have kind of a standardized setup of that, which we can provide to the integrator or to the end customer and quickly get to business there. Yeah, we recently, a few years back, we bought Swisslog. We are very good. I feel like I have a few projects with Swisslog also. I think it's very good cultural fit also, so we have a lot of logistics solutions there, and of course China business, as you know, KUKA was bought to a large percentage by Midea China, so we have a large ramp up at the moment of production and also development in China, and looking into more China market specific products, which are a little bit different from what the German automotive manufacturer, for example, expects. And yeah, wherever you are, I think we are close to you. And I mean, we have very good support, so to say, very good reach of support. So if there's a problem somewhere, I know a lot of colleagues in Augsburg that regularly fly out to Brazil, to China, wherever. And that's our daily business. So yeah, we're not very, like, we're very market agnostic, like we'll do business anywhere. So as you know, KUKA doesn't have just like 1 or 2 different robots, but we have a lot of different robots. And on top of that, we have those linear rails, and we have this positioners, so extra axes that are also controlled by the robot. For example, if you want a rotary table for welding or something. And there's a different areas, so we have waterproof robots, hygienic machine for food processing, clean room, explosive environments, and all this. So it's quite a lot of different robots, which of course makes the task of like finding one ROS driver for everything is maybe a little more difficult than for other players. You can find all this in CAD publicly, so it's not too hard to make a URDF model. Of course, at some point we want to be able to provide URDF models ourselves, which would be easier for our customers also, right? And on the other hand, there's a large part of KUKA now, which kind of started in corporate research. It's kind of like a corporate research graduate, the mobility. I think, I'm not sure, I wasn't there back then, but I think we started around about like 2005, 6, 7. And now we have a lot of platforms in the field, especially also in aerospace manufacturing. And these range up to 30 meters of length, 90 tons of payload per platform. But we also have applications where we're docking 3 platforms of 30 meters length to make one that is 90 meters long, especially like in airspace fuselage assembly. You can have like the front part, the middle, and the back of the airplane, and then position it very precisely and put it together. And you see on the bottom right, also we're doing mobile manipulation. And that's what I want to talk about today, but not for this one, but actually for the KMR EVA. So as I said before, you can see the basis for the TUM ROS-I on the very left. So this was a prototype. You see there's like Baumüller, servo drives and all. This is kind of like a outside technology for us. And then on the bottom right, you see what's the current product. So it has been quite a, an evolution that went through several technology readiness levels, and now only like 10 years later, we have a large-scale fleet actually running at customers on the line, and we have milestones like these guys have to run for 20 days consecutively without any problems, which was not the case in 2007, as you can imagine. And there have been interesting projects. So one thing like here, the 2010 version, so to say, this was also in the clean room at Infineon. Starting, I think, 2013 to 2016, we had projects of wafer handling. And then you can see a little bit the scale of, or the time scale of such projects. 2013, we started doing clean room, wafer box handling, or these wafer pods. And now 2018-ish, we are at the customer with a product. And we pushed for all this time. Why did we choose this? Of course, this is a business where we have 24/7 operation, and the cost of a failure is very high. So we have customers that say, if you drop a pod of wafers, these wafers could have been in the process already for 3-4 months. Like not in a standard whatever chips, but in some applications. And then if you drop that box, you have to start over, and one of those wafers can be worth 20,000-30,000 euros, and you have a stack of 20 in one of those boxes. So it's not a very hard job for a human to do. But if you have a failure, the cost of failure is very high. And of course, on the other hand, the investment of creating a fab for semiconductor manufacturing is very high. So the manufacturers want to keep them going for a very long time. And initially, if there's a new process, they'll have very high margin, and they'll hire everybody at any price to operate that, or they go for full automation. That's also happening. But then later, like, of course, they want to keep it running at a lower cost, and then they're looking into automation after the fact. So we are going into semiconductor factories, fabs that are not meant for fabrication from the beginning, where humans were operating, but then at some point it gets cost prohibitive, or the humans are going to a new fab, and we're trying to automate this after the fact. And that's a very nice business because the margins are still very high there, and the customers are used to very high investments that will only pay out after a long time. So that was our natural choice to push towards that as a first application, also including this sensitive arm, which can be very, that can feel the touch, and we can, we can very carefully move those boxes and detect if we have a collision with something unknown, like let's say a load port is closed when it should be open. We don't just push through like with an industrial arm, but we will notice, oh, there's an obstacle, and stop without destroying anything. Yeah. So let's see. Yeah, some requirements are a little crazy. Like the first guys in this area said, you have to position your mobile robot within 1/10 of a millimeter, which is difficult, obviously. So we addressed this, and you see also coming from the prototype to the product, we changed a few things. Of course, we've profited from the battery technology. We've had some issues, like you see this black and orange platform there. There we had problems with the battery, so we had to kind of restart, and then we decided to make it a little smaller already, get this clean room spec, and actually we also transitioned from having timing belt transmission for the wheels, and now we have cycloidal gears, which are also used in our robots. They're backlash free, and they help us to position very precisely. And yeah, of course, as things have come closer to product, also things have closed up a little bit, not so open anymore. In the beginning, we had those Baumüller servo drives, and anybody could connect, like everybody could just look up how to connect to those servo drives, and now we're using our own stuff, and it's all a little bit more close. And now, of course, I'm in corporate research, so I'm always collaborating with research partners on these platforms, and a lot of them want to use ROS. They want to command this with ROS. So this was inspiring to actually write a ROS driver for that. So here's just a few projects that we're doing in corporate research. It's not all of them, but you see the ones with the star on the right side are projects where we did use ROS for some part or the other. And I wanted to speak today a lot about this hybrid project. I just want to scroll a little bit into it. Unfortunately, how do you say oh, I don't know how to skip. I'm sorry. I can't skip the time. So unfortunately, we just had the final presentations and the videos are not finalized yet. It's not out for public. The idea is that we have a dual arm platform here, and the idea is to bring, like in an automotive kitting kind of situation, to bring parts that are a little bit heavy for the worker to the assembly line. So we have the car bodies on the assembly line, and actually these car bodies in this case are moving on a conveyor. So the person takes the part, goes onto the conveyor, and then the conveyor takes him along, and then he has to mount the part. And now we wanted to automate that a bit, and that's a typical Volkswagen project, because there we said we don't want full automation, but we want to help the worker. So the robot is sensitive, and he will bring the part to the place where it has to be mounted, and then the worker can actually touch the arms, position the part precisely, put the screws in, and then give the robot a tap, and the robot will go get the next part. That's kind of the thing that you see a lot in Germany, where you have workers' council and things like that, where there's actually a lot of money spent, not for full automation, but for those kind of collaborative efforts. And yeah, I wanted to skip a little bit into, but I think considering time, I'll just go forward. A small disclaimer, of course, in research, I see a lot of people that don't know what safety means yet. And I've been at customer sites where you see a robot move in a room and there's a few students, but you don't see the guy operating the robot. You don't see the guy with the e-stop. And then you find him in the office somewhere, maybe looking at ROS, and he say, yeah, I see the robot move here in ROS, but he doesn't see the people, right? And that's not safe, actually. So that's the problem that we often see, that research partners are not so aware, especially academics, about what safety means. And I just want to say a few words. In our research corporations, often we have to make our partners sign an agreement that says, hey, I'm aware that this is not perfectly safe like a product, but you have some extra functionality that KUKA provides that actually puts it outside of the DIN spec or whatever safety specs is there. And then, of course, we have to have our partners sign that they are aware of that, and we have some extra rules like laboratory setting. So we always have to have a person that is a trained professional that knows the application, hold a e-stop in the mobility case, a remote e-stop, observe what's happening and stop the robot in case something's going wrong. And of course, this is for research, and then later, if we know, okay, what could our product look like, then we can think about how to make it safe, and also how to get through all the quality gates to actually be able to release as a product, because this would slow us down in research. Like if you release a product, you can imagine there's a lot of, like we have a lot of quality control and quality gates before we can actually push out a release. We can't change a few lines and deliver it tomorrow. It's quite a process. So yeah, this thing said, now let's see how we close the language gap between KUKA and ROS. I just want to go back to a little bit, like, what do we do with those more industrial arms? There's this KSC4, KSS arms. And in ROS-Industrial also, you see there's a lot of drivers, and there's, just a second. There's basically two things that you want to do usually, and there's one interface that's called a robot sensor interface, which gives you 250 Hertz real-time control from an external controller. And on the other hand, there's this Ethernet KRL interface where you can, in KRL, which is the programming language for these KSS controllers, it's a little like Pascal, and it has some interesting features. For example, it's interpreted in the real time. So we have a language that's interpreted in real time, means it's actually behaving quite deterministically, which is not often the case for such things. So we have this interface where we can just send XML messages from external, and then you can interpret them on the controller in the real-time system, and then of course you have access to all the functionalities like LIN, PTP, spline, and these are these two classes of drivers for those robots with KSS. There are other interfaces like this MX automation. Sometimes the question comes up, should we use that? But I think that MX automation is like a subset for CNC controllers to do like loading of a CNC machine. It doesn't support the full capability, so I would rather go for this EKI or RSI. EMI is actually the same thing as RSI, but it's kind of the underlying system. ROS-I is well documented. EMI is more like an internal thing. And if you're using ROS-I, you're actually using this EMI. And then on the other hand, we have those Sunrise robots. Sunrise is a different controller. It shares some of the technology. And there we have Java as a program language. And we actually have this thing called VxWin. So on the controller, we have a VxWorks real-time system. But on the same CPU, we also have a Windows running. And on this Windows, we have an so-called application server that runs a Java application, and the Java application then speaks via TCP/IP to the real-time system. As long as you're on the controller, on the Windows side and the VxWorks side, it actually goes through shared memory. So we have a Ethernet, a network driver that is using shared memory. But on the other hand, if you are putting the application server somewhere else, it just works the same. So it's TCP/IP. So you can do a little bit of cloud robotics, so to say. You can connect a lot of robots to one Java program and control them all from one program via TCP/IP, which is interesting. And then again, we have this like EVA stack from TUM, IFL, which supports PTP, LIN, but also servoing motions in soft real time. So they were talking about like 20, 30 hertz control, and soft real time it's in Java, right? On the other hand, we have this FRI, the fast research interface, or now fast robot interface, which allows you to control the robot from an external PC that should be a real-time system with 1 kilohertz, including torque control and all those things that you would want to do. And one thing that I'd like to add is often we ask like how to integrate PLCs in my ROS system. Actually, we have a thing called Work Visual, where you configure how you want to have the signals on your PLC interpreted or how you want to send them. And then if you click a button after configuring, you get Java code in your Java program. And actually, with ROS Java, you can put a ROS interface on top of that. Currently, we don't automatically generate a ROS interface. It would be something that is possible, but we have to see if there's a market for that, right? And yeah, these are the classical things that are done, and you saw a lot of KUKA robots in the last presentation and the other presentations that were using one or another of those technologies. Now let's talk about the mobile case. So we can control the robot on top of this, but what to do about the base? And if you're looking back at ROS-1 move base, you see that if you look at the outside there, you have AMCL, and then you have these TF messages with where are my sensors, you have odometry messages, you have a map somewhere, sensor topics of the laser, and you have a command velocity. And looking at our KUKA system, it's actually quite similar internally. Also, it's kind of originating from the same group in Freiburg with Wolfgang Burgert. The difference is, so we have an extra PC that runs the navigation software, and we have a lot of nodes that are very similar to what is running on the ROS navigation. The difference is we're using something very old, CMU IPC. So it was first introduced in '93, made for NASA projects flying to Mars or something. Still works, so we've been thinking about changing it sometimes, but actually it works quite fine. And so what we do to interface to ROS actually is just kind of converting IPC messages to ROS messages, which is a very simple thing to do. So we put a ROS adapter there that has IPC and ROS knowledge, and then there we're just like, interfacing. There's a caveat, so if you're looking at IPC and if you're smart with IPC, there are some parameters where you can say, just please log all IPC messages, dear IPC server, and you'll see a log of all messages and message types. And then maybe if you're very smart, you'll find the topic that actually commands the robot. And then you'll find out if you're publishing on that topic, the robot still doesn't move, because we have another safety mechanism that makes sure, like the single point of control, that we have kind of a registration of who's in command of the robot. And like this can be easily hacked so that you get all the sensor signals. But if you want to drive the robot, of course, please speak to us. And anyways, we don't put this out in public for some reasons for now. And we try to be in close contact with people that want to use it. And especially if you want to have the use case where you're commanding the robot with ROS, it's a different level. Of course, if you're only looking, if you just want odometry, laser signals and such things, it's not really unsafe to do that, right? So that's something that we can give away more easily than something very controlled by us. And like looking at the messages is very similar. Of course, it's just like the laser message. So here on the left, you have a ROS message, and then you say there's an array of ranges, and it's just the same in IPC. Basically, you have an array again where there's many ranges. It's a little different, of course. On the right side, we have a config message that tells us what is the range and range max, range mix, min, what's the time increments and all this. So of course, it's a little different, but it's not too hard to convert. And the one thing that is generally a tip for like connecting systems, we've seen a lot of people out there in research, especially a lot of universities have their own frameworks and now they want to connect them to Java. And sometimes they come from a real-time world where everything is done maybe in one thread and there's not much synchronization, and then sometimes this fucks up if you convert it just one-to-one to Java. So we would always recommend to use this kind of blocking queue mechanism where you have a listener thread and a publisher thread, and then in between you have a thread-safe queue, and that just makes it a little, how to say, easier to work with. And then actually what you can do is, like, if the listener puts something on this queue, the publisher thread will be woken up. And then you can check also how many messages do I have in my queue, and if you see there's more than one, then probably something went wrong. You will stop somewhere, and you can maybe send a log message that there's some problem and you should look at it. And so that way we had so far the best experience doing it like that. And it's very, very easy in Java. So you just like create this queue, and then in one thread where you're listening to IPC, you just like, here we are creating the ROS message in the IPC thread. You could also create it in the other thread, doesn't really matter. And then you're putting it on this queue, and that will actually notify the other thread. And in the other thread, you're just doing this, just doing this take, and then you have your message, and you're in the thread where your publisher is running, and you don't have to like think about wait and notify and mutex and all this. It's very simple in Java, I would say. Time synchronization is always a topic. Unfortunately, it's not so easy. So VxWorks, I have to speak with Andre if he's still here. He's very knowledgeable, I guess. So VxWorks has its own real-time clock. We have a PTP server. So PTP is precision time protocol. So in principle, you can, for example, you can buy a camera that synchronizes with PTP. And the difference to NTP is it's just like orders of magnitude more precise. But our PTP time doesn't run synchronized with UTC. You cannot externally synchronize it easily. So what we do most of the times for easier applications, we just stamp ROS time now when we receive the message on the Java side, which is of course not perfect, but works for most things. So we just put a stamp whenever you receive the message, and that's often close enough. You can get, so that's a little bit, maybe the topic is like the title is not perfect here. So in Java, we have this Robotics API that provides a lot of functionality in a very easy to understand and use API. But sometimes if you want to go above that, of course, all the communication with the controller is also in Java, and we can kind of make add-on functions. For example, here I'm saying, okay, give me the time of the controller, the current time, and the controller can also do the same for like if you're creating the joint state or if you're creating the odometry, and then you can have applications work better. For example, you have a sensor, like a camera, and you're doing some inspection task, and now you want to know where was my camera when I took the picture, and actually we can show you how to get the joint state and the odometry state at a very high frequency with the PTP timestamp that your camera also synchronizes to. So if you have questions in this direction, please contact us. We can make it happen. It's kind of a rare thing, so it's not included in the general robotics API for everybody, but it can be added just in the application. And yeah, of course, a lot of times, if you put too much into your Java program, into your robotics API application, it could be that the CPU is overloaded. And we don't see this too often, but what you can do, of course, if you're in ROS, like you usually want to move CPU heavy loads on another PC. You have a ROS PC somewhere, like let's say you're doing some vision task or something. You don't want to do this in Java on the robot controller, but you want to do this externally and then message. It is in principle possible also to run the application somewhere else than on the controller, which is not officially supported. You can see here how it's done. It's a single point of control issue again. We had customers that do this, and then they copy some configuration file, and one guy starts a program, and then somebody else's robot moves because he had a wrong IP in his settings, right? So you have to make sure that you're not running into these issues. But this can also be used. I mean, for example, DLR would do this, like they had an Eclipse in Linux where the application would run, or you can just do an executable jar somewhere, and that is a possibility. As I said, it's not really meant for production. Then Java performance is sometimes an issue, so there are some good tools, GC Easy. We recommend to do that if you're in production, like we are running those 20-day tests, for example, and then you're just logging what the garbage collector is doing, and there's very nice GUI on the web where you just upload the log and you get a lot of information. Yeah, and one last remark is like TCP performance. We have a lot of people that say, oh, my Windows gets to command very slowly only. So Windows is optimized for throughput. And there are some settings, this TCP X frequency and no delay for TCP that you can set, and then the packet latency is much lower. So for example, we could query the odometry from the real-time controller, convert it to ROS, and start a ROS listener on a different PC in the system on Linux and get the odometry with 600 Hertz with this little change. And if you don't put those changes in ROS, then in the Windows PC, you'll only see 20 Hertz maybe. Okay, so concluding, I'm sorry I took a little more time. Many robots are today already used with ROS. Of course, it's not perfect that we're not publishing official drivers. We're trying to get there. Now we are starting in cooperation with KUKA Hungary, where we have a little more resources to do this. It's not so much of a problem of writing those drivers as management sees the problem that a lot of people will call support with ROS questions, and they're very scared of that. So it's a little bit of politics, but I think now we are in a position where we can actually push things again, and I think very soon, I hope that we'll get some official drivers. And of course, I would ask for help here. If you're a user of a KUKA robot with ROS, or you want to be a contributor, please get in touch. Also, if you want to buy a KUKA robot and you need ROS, please tell sales. It always helps to tell them, because sales is really the biggest lever. If they call us and they say, oh, I can only sell this robot if we provide a ROS interface, that helps us also to allocate those resources. Okay, thank you very much. I don't have a ROS at KUKA.com yet. I'm trying to get it. So far, you can contact me with this email, and I'm open for questions. Thank you.
Thank you, Thomas.